Hello, and welcome to the IMFs and electronegativity video. So we'll eventually be talking about intermolecular forces, and they're incredibly important for those of you guys who are interested in going into studying healthcare more. And the reason for that is a lot of materials in biochemistry are heavily influenced by these intermolecular forces. So the intermolecular forces are what hold DNA strands together. They are what cause proteins to fold. They are what cause some medications and vitamins to be fat soluble versus water soluble. And of course, they might be just a little important to chemistry as well. So kind of important stuff. So before we get to that, let's talk about electronegativity. And electronegativity defines an atom's ability to attract bonding electrons to itself. So essentially there's two different ways that we can bond. We can either share electrons to make a covalent bond, or we can exchange electrons to form a ionic bond. And the way we determine which one of these types of bonds we're going to form, or even what type of covalent bond we're going to form, has to do with this electronegativity. And what we see is it tends to be high for the nonmetals, and it tends to be low for the metals. And so if we take a look at a periodic table here, we have a bunch of values listed. So fluorine is the highest element. Fluorine has a value of 4.0 by most people's scales. And you'll see slightly different values, or sometimes slightly different scales from textbook to textbook, because these are experimentally measured numbers, and therefore there's some error in them. But we're just going to work with the values from our textbook right here. So our values are highest in the upper right portion of the periodic table. That's where we're high. And we're lowest in the lower left. So over here we have cesium having our lowest electronegativity, or our lowest attraction for shared electrons. And you might notice something here, and that is that the noble gases are left off the list. So you might be wondering, well, what's the deal with the no noble gases? Well, you notice that the electronegativity refers to bonding behavior. And so what we see is the noble gases, because they don't really form bonds, we don't really tend to measure their electronegativity, because electronegativity, again, talks about how things behave when they bond. So right here we have a handy trick for remembering the top 6 elements in terms of electronegativity in decreasing order. And you can remember this as phone, call, break. So FON, phone, CL, call, BRC, break. So phone, call, break. Fluorine is the highest, oxygen's number 2, nitrogen's number 3. It's very important, there's our top 3. Then chlorine, bromine, and then finally carbon. So how do we actually use these electronegativity values? Well, we got some really simple math. We're just going to use subtraction. So we're going to look at the difference in electronegativity. And so if our difference in electronegativity is very small, so in other words, if our difference in electronegativity is anywhere from 0 to 0.4, that means that we're going to form what's known as a nonpolar covalent bond. And so this means that we have equal or almost equal sharing of electrons in our compound. And so if we look at a nitrogen-nitrogen bond, for example, nitrogen has the same electronegativity value as nitrogen, and therefore our difference here is 0. If we compare chlorine and bromine, chlorine has an electronegativity of 3.0 and bromine an electronegativity of 2.8, and so our difference here is 0.2. So it's a very small difference. It's still within our 0 to 0.4 range. So this one's also nonpolar. And again, same deal with hydrogen and silicon. So I want to point out, you don't need to memorize these electronegativity values. These will be given to you if you need them on a quiz or exam. And so again, don't bother memorizing them. You can look them up if you need to. But you do want to know the trend for electronegativity, where it's highest in the upper right of the periodic table and lowest in the lower left. So our next type of bond is what's referred to as a polar covalent bond. So it's still between nonmetals, and we're still sharing electrons, but we do not share those electrons equally. So one of the elements, the one with the higher electronegativity, is going to pull the electrons towards itself. And that's what this sort of cartoon drawing over here is trying to indicate. If we look at chlorine and hydrogen, chlorine's got a much higher electronegativity, so it's going to pull those electrons towards itself and away from the hydrogen. Not enough to make an ionic bond, but enough that they're not shared equally. And so if our difference is in the 0.5 to 1.7 range, then the resulting bond will be polar covalent. So if we just pick one of the examples from our table here, if we take oxygen with a value of 3.5 and sulfur with a value of 2.5, again, don't bother memorizing these. You'll be given them on quizzes or exams. and our difference is 1. And so that's sort of right in the middle of our 0.5 to 1.7 range, and this would indeed be a polar covalent bond. So we're still sharing, but not sharing equally. And then finally, we have our ionic bonds. So if our difference in electronegativity is 1.8 or more, then we're no longer going to share electrons, we're actually going to exchange electrons. And this tends to occur when we bond metals and nonmetals to each other, because the metals are so much lower in electronegativity than the nonmetals are. And so, for instance, if we look at potassium and chlorine, chlorine's 3.0, potassium's 0.8, our difference here is 2.2. And so therefore that's within our ionic range because it's greater than 1.8. So again, no more sharing of electrons. This is when we have electron transfer. And so here's a diagram sort of illustrating what these bonds look like. Our atoms are sort of mushed together here in their sharing of electrons for the nonpolar covalent bond. And then as electronegativity difference increases, the electrons are going to sort of pool towards one end of the atom. So this end of the one end of the molecule. So this end of the molecule is more rich in electrons. It's higher electronegativity. Then finally, if our difference is big enough, we see these are no longer mushed together. They're not sharing electrons anymore. This is when we end up with an ionic bond. So please pause the video and complete questions 1 and 2. Welcome back. Let's talk about our 3 different types of intermolecular forces. So the intermolecular forces, we're going to determine which type we have based upon the types of bonds in our compounds. So if we have a covalent compound, and our covalent compound's got polar bonds in it, then we end up with what's known as dipole-dipole attractions usually. So again, molecules containing polar bonds tend to form these dipole-dipole attractions. And so what we see is one end of this molecule is kind of negatively charged. One end is kind of positively charged because the chlorine is much higher in electronegativity, it's negative, and the other one's kind of positive. And if we take another molecule nearby, those opposite charges are going to attract each other. So between these molecules, inter means between, so between these molecules we have our IMF, our intermolecular force. And so these are much weaker than covalent bonds, but they're still very important because they're going to determine the physical properties of our compound. So these polar hydrogen chloride molecules are attracted to each other through these intermolecular forces because of the polar bonds inside of them. Now, another type of dipole-dipole attraction is what's known as hydrogen bonds. And so one of the things I should point out about hydrogen bonds that's really important is these are not actually bonds. So the name is confusing here. The hydrogen bond should really be called hydrogen attractions or hydrogen forces, but the name stuck years and years ago, so we still call them hydrogen bonds. And so these are not covalent bonds, these are actually attractions between the molecules. They're a type of intermolecular force. And so it's the same thing as dipole-dipole attractions, except these molecules are extrapolar. And so the reason for that is that they contain nitrogen, fluorine, and oxygen, and that has to be attached to a hydrogen atom. So if we have nitrogen, fluorine, or oxygen attached to a hydrogen atom, and we have lone pairs on that nitrogen, fluorine, or oxygen, what we end up with is extremely polar bonds. And that's because nitrogen, fluorine, and oxygen happen to be our 3 most electronegative elements. So 3 really electronegative elements, big electronegativity difference, high polarity, which is going to give us this extra strong dipole-dipole attraction known as hydrogen bonds. So again, it's these attractions between the molecules here. The hydrogen bonds are not inside the molecule. They're not covalent bonds. These are actually our attractions between molecules. I know it's confusing, but do remember hydrogen bonds are not actually bonds. Our last type of IMF is when we have molecules containing exclusively nonpolar bonds. So in our nonpolar molecules, we have what's known as these dispersion forces. And so dispersion forces are the result of temporary polarity. So if we look at, let's say, this atom right here, on average it's nonpolar because the electrons are evenly spread around. But at any given moment, because the electrons are in motion, our molecule might be, or our atom might be, in this case, temporarily polar. So this thing is polar at this moment because all the electrons just happen to be at one side because of the random motion. And I forgot to mention the previous slide, these little tadpole-looking things, these are the Greek letter delta. And that's meant to represent a partial charge, so essentially a charge that's smaller than that which we'd see in an ionic compound. And so right here we have, if we take one of these nonpolar molecules and stick it next to another nonpolar molecule, the electrons can move around in such a way that we can end up with temporary dipoles. And what that means is essentially these molecules can be temporarily polar because the electrons just pool in one end. And so we end up with these temporary attractions that we call dispersion forces. Now, some people call these London forces, some people call them London dispersion forces, some people call them van der Waals forces, but let's just stick with calling them dispersion forces. But be aware, you might see other names for these things. So here's our summary right here. If we look at our ionic bonds and our covalent bonds, these are very, very strong. These are hundreds or thousands of times stronger than intermolecular forces. But between the molecules, we have hydrogen bonds, which are our strongest IMFs, because that's where we have the biggest, our largest polarity of our molecules. We have these dipole-dipole attractions, which are our second strongest, or sort of medium strength IMFs. Then finally, the dispersion forces, which tend to be the weakest, because the charges here are just temporary. These temporary polarities of these nonpolar molecules because of the motion of those electrons. So why should we care about the IMFs? Well, again, I mentioned they're incredibly important to biology, but in chemistry, they are going to control the physical properties. So what we see is if we have stronger IMFs, the result's going to be higher melting points and higher boiling points. So in other words, our material is more likely to be a liquid or even a solid at room temperature if our IMFs are pretty strong. And if we have weaker IMFs, then we're generally going to have lower melting points and boiling points, and that means oftentimes compounds with weak IMFs are going to be gases at room temperature, or at least they're going to boil and vaporize easily. And so when we change states, we change physical states like solid to liquid, liquid to gas, gas to solid, those IMFs are due to change, or those changes are due to IMFs changing, not the bonds. So the bonds themselves don't actively participate in these state changes. So for example, when you boil water, you break the hydrogen bonds, but you do not break the covalent bonds. And polar compounds, those with strong IMFs, tend to be soluble in water. So like alcohol is soluble in water, sugar is soluble in water. Those are compounds with strong intermolecular forces because they're very polar. And then nonpolar compounds generally aren't soluble in water. And so examples of that would be like gasoline or like olive oil. Gasoline or olive oil have weaker IMFs and therefore they do not dissolve in water. And solids tend to have stronger, or excuse me, if we have a solid, typically the stronger the IMFs, the harder the solid will be. So what we see is something that crumbles really easy, like talcum powder, is going to have weaker IMFs than, say, something that's very rigid. So great work, you survived the video. I'd like you to now end the video and please complete questions 3 through 5. Thanks.